So now you're in the world of parametrics, and we're entering into the world where parametrics combines with motion and vectors. But let's think back to when you were young and naive. Remember when you used to use position function, velocity functions, and acceleration functions in rectangular form? Well, we're going to use this to create an analogy to hopefully help you understand vectors if you don't already understand vectors. And when you looked at these items, these gave you basically a general formula for position, velocity, or acceleration at any time t that you cared about. If it so happened that you cared about a specific time, then you plugged it in, and because you respect symbolism, you wouldn't just write v of t equals this, you would write v of 3, because now we're looking at a very specific information, or a very specific spot in time. So keep in mind that we kind of had a general velocity equation, and then we had a specific velocity value for a specific time. And we could do these same things with position or acceleration. So the same idea, the general information and the specific information, can be applied to vectors in parametrics. So here's a situation where, say, a particle is traveling through outer space and its x and y values for position, in other words, its coordinates, are defined parametrically. So you would call this the general position vector. And a vector with position doesn't seem to make a lot of intuitive sense because most people think about a vector implying some sort of motion. But let's just get over that for right now. This is the general vector for position, and then if I cared about position at a specific moment in time, I would plug the 4 into there, and now I would have the specific position vector. So be careful if you're ever reading through a situation. Are they in search of a general vector or a specific vector? Now I know the location of my particle. Well, of course, calculus doesn't change. Thank you, Newton and Leibniz. So the derivative of position gives me velocity. So I could use this type of notation to say I've taken the derivative of my position locations. But the same thing's going to happen in vector form. If this was the general position vector, then each piece has a derivative. Now we have a general velocity vector. And if I were concerned about, say, the velocity at t equals 4, I could go ahead and plug a 4 into here. So keep in mind, again, the difference between a general vector and a specific vector. And we're going to soon talk about the information this one gives us, because it gives us a lot of good, juicy information. Then, as you would guess, you could take your velocity vector and you could go one step further, get yourself an acceleration vector. And from here, you could do maybe some comparisons between the velocity and the acceleration at a specific time. And you could determine things like speeding up, slowing down, traveling left, traveling right, things like that. But what I'm going to do now is take a look at what information does this specific velocity vector give us. So that was our velocity vector, and that was taking place when the particle was at this position. So I'm going to give you a not so accurate graph of this situation. Roughly speaking, the particle is at 64, negative 128. So we'll say that 64, negative 128. That's its position. But what I'm concerned about now is our interpretation of what's going on with the velocity vector. This part is the component of travel that relates to the left and right because it's the x part of your velocity vector. So that means if my particle was right here, its velocity influence is 32 units to the right at that instant. But the velocity or the horizontal component of travel must also be combined with the vertical component of travel. So at that instant, the particle is also heading downward at that many units or meters per second. So if I think about it like you might in physics, this particle has a force that's shoving it this way by about a factor of 32, and a force that's shoving it this way by about a factor of 96. So if I would connect this to this, I would get the particle traveling in that direction. And we're going to talk later on about how we could find the actual speed of that particle. But keep in mind, this is basically this information telling me a specific direction of travel at the instant t equals 4. The reason I didn't necessarily make this go all the way down here is because we would have to recalculate at t equals 4.01, and we're going to have a slightly different vector. And if you just keep computing at each new location, you're going to get a string of different vector forces and probably giving you something curvy. Two things you should really feel comfortable with is the difference between a general vector and a specific, and then what information is this specific vector giving you.